Welcome.
The Pathology Innovation Collaborative Community is a regulatory science initiative that aims to facilitate innovations in pathology, as well as advance safety and effectiveness evaluation. The PI Collaborative Community aims to harmonize approaches to speed delivery to patients through collaboration in the pre-competitive space. The PI-CC is open to all stakeholders, public or private, including but not limited to academia, industry, healthcare providers, patients, and advocacy groups. Meetings of this kind are an example of lawful activity under federal antitrust law, because the focus of the meeting is on government action or policy, including the industry's responses or positions taken with respect thereto. However, antitrust monitoring is needed for companies' own protection, since they are direct competitors meeting together. These meetings need to stay within protected subject matters and need to be monitored so that they do not stray off into inappropriate areas, such as pricing and price terms, sales and service territories for particular products, customers and customer territories, each company's individual decisions regarding selection of suppliers or customers, marketing plans and especially future marketing plans or new product offerings, other proprietary or competitively sensitive information. Today's meeting will follow the written agenda, and there will be no discussion of pricing or other prohibited topics. If the discussion veers into those topics, we will terminate the discussion. If you have any questions or concerns about the propriety of a discussion, please raise it immediately, and we will take a break to determine how best to proceed. The Medical Device Innovation Consortium acts as the formal convener, and we will follow their conflict of interest policy. For additional information, we defer to our Code of Conduct and our website, www.pathologyinnovationcc.org. We look forward to moving the field forward.
Well, why don't we get started? Because I think we have a lot of topics and content to cover. So it's my distinct pleasure to introduce Dr. Umeton and Dr. Rosenthal, Renato and Jacob, of course, to this session with Pathology Innovation Collaborative Community. Of course, as any time and any event, we record this and put it on the website, and I'm particularly thankful that you allow us to do so. So Jacob or Renato, I don't know who will start, but thank you so much and welcome.
Thank you so much, Joe, for the invitation. Thanks everybody for tuning in. So today we're going to talk about PathML, an open source software toolkit for computational pathology. I'm going to start sharing my screen and I'll click slides. Okay. Please tell me when you can see my screen. Should be up in just a moment.
Yes.
All right. Excellent. So welcome again, everyone. And generally, people start with the why and everything, and then have credits at the end. I want to start with the credits here. The mastermind of all these is Dr. Massimo Loda. He is a chair of pathology and laboratory medicine at Weill Cornell and pathologist in chief for NYP. He was previously at Dana-Farber, where we started our collaboration. And he really had a vision for what AI, data science, and pathology could do together. And when we started working on it, we realized that we were not as far ahead as radiology in terms of software and code that is available. We were rather behind. And so we realized that there was really a gap to fill. And so Ryan, Jacob, myself, Massimo worked with others, including David Mohan, Karen, Luigi, and many others from the open source community to really put together PathML. Quick slide of background about myself. I studied computer science for master and bachelor. After that, I got a PhD in mathematics and informatics. Long story short, after working in academia, in consulting, many other roles ranging from postdoc to director, I joined Dana-Farber Cancer Institute in 2016, where I report to the Chief Data Analytics Officer. I still consider myself a researcher at heart, in the sense that I'm still helping researchers, and that's why I'm also affiliated also with MIT, Harvard, School of Public Health, Cornell. I published a bit, worked on a few patents. One of the things that really gets me excited is this last line, co-chair of Medical AI at ML Commons. It is an organization whose sole objective is really benchmarking AI. When people say, oh, state of the art, what does that mean, right? We all read state of the art in a paper. In AI, in the medical domain, is very complex, and there is a very nice synergy between them, possibly, and everything that is happening also in digital pathology. By means of introduction, the group that I lead at Dana-Farber, it's basically professional services for AI and machine learning. We help researchers who have a need in these topics. We focus mostly on natural language processing as a type of input, as well as images. And that is pathology images, radiology, radiation oncology, and alike. So we do a lot of computer vision and similarly. In general, we want to help people who are transitioning from X, whatever that is, to AI-powered X. Now, how's that is relevant to AI and machine learning? When you think about how much work you need to really put AI and machine learning in production, this is true for every industry, really. The AI and machine learning code is, 5 to 10% of the effort. Everything else is adjacent systems. In other words, when you really want to support AI and ML big scale, you have to worry about so many things. That is particularly true in digital pathology. So when we started, we thought, all right, we're gonna climb a mountain, we're gonna apply AI to the pathology realm and do something amazing, right? There is a mountain to climb and looks pretty much like it. In reality, it was more like that. There was another set of mountains to climb before we could even get started, and that was all related to data engineering. What I mean by data engineering in digital pathology is the following. First off, we had to load the images. And in radiology, you have about 2 data formats that account for 80 to 90% of all images that you encounter. In pathology, it was 180, and that drove us crazy. So then once these images were read, we realized, okay, now we have to do the pre-processing, detect the artifacts, remove them, normalize staining across scanners, and then tiling. What's that? So basically, these images are very large. They don't fit in any computer memory, so you have to slice them up. There are many ways to do it. And you want to distribute the compute. You want to use clusters or the cloud. And again, many ways to do all that. Once you're done and you have to iterate all of these, you have to start benchmarking. And again, you are maybe identifying a cellular component of interest, or you're quantifying stroma, you're counting cells of a specific type, and so on and so forth. So you keep iterating this process. Then you want to give your pipeline to your collaborators, or you want to publish it as part of a nice publication you put together. That is also quite challenging. So grand total, we were looking at anything between 10,000 to 50,000 lines of code just for steps 1 through 6. And they required a lot of iteration. Every decision we made at every step influenced everything underneath. It was basically always bifurcating for us. And so we realized we really need to implement computer science and software engineering best practices. And this is how PathML was born. In a nutshell, PathML is a Python software library. Is released under an open source license, which makes it very friendly for researchers. It aims at supporting end-to-end digital pathology workflows, and it's a low-code type of software library. That means that you really have to write very few lines of code in order to get started. When possible, makes industry standard choices for you, uses best-in-class algorithms. It's highly modular and extensible, meaning you can easily build on top of it or change things as need be. In other words, it allows you to focus really on the research part and takes care for you of all the data engineering needs. We thought we were the only ones with this problem, but actually when we open sourced it, there was a lot of interest, a lot of excitement, and people, as Jacob will show you in a moment, are really starting to use this library and give us phenomenal feedback. Few examples, some pipelines that were in the 10,000 to 20,000 lines of code now are reduced to 15, 30 lines of code using PathML. A codex pipeline, some of you might know, are quite complicated. We were working with one of these pipelines that used to take 2 days and require about 100 clicks. Now it requires 1 click and it runs in 2 hours on the same hardware. So this was the introduction. With that, I'll pass it to Jacob, who has been working hands-on on this library, and together with Ryan, really built a lot of the functionalities, and he's really, the prime and lead author around this library. To you, Jacob.
All right, thanks so much. Do you want to stop your screen share so I can put up my slides? Okay, one moment. All right, great. Yeah, so thank you, Joe and Ua, for inviting us to speak here today. Really excited to share. Renato kind of laid out the high level background, and then I'll kind of dive a little bit more into the nuts and bolts and some examples. But yeah, really excited to be sharing this with the Pathology Innovation Collaborative community. Yeah, so first we just wanted to start with kind of laying out, how these types of tools kind of fit in with this larger transition to digital pathology. So I'm sure I'm kind of preaching to the choir on this one, but just so we're all on the same page. So the current, state of kind of analog or manual pathology is where the specimen's just mounted on a slide. Pathologist looks at it under the microscope, like a physical microscope, looking at a physical slide, and then that's what they use to decide on, the care or the treatment strategy for the patient. And so when we think about, this transition to digital, basically we're seeing that, there's this extra step of, once the specimen's mounted, then the slide is actually scanned at extremely high resolution. And then you end up with this kind of database of high resolution scanned images. And then the pathologist can actually look at these images on, through software. Of course, they can also still look at the physical slide, but, this is kind of the transition to digital pathology. And the reason why we're so excited about this, from the data science and AI and machine learning side, is because once we have all these images digitized, we can actually start, training machine learning models and, making tools to help pathologists with, detection, prognosis, quantitation, etc. And so this here in yellow is kind of like what we're working towards, and the future of AI integrated pathology. So just wanted to kind of lay the stage there. So when we think about big data in pathology, I wanted to spend a couple minutes talking about what does that actually mean, because something that's pretty interesting is that we're actually seeing data growing exponentially in pathology, but in different dimensions. So the first dimension that you might think of is just number of images. So we're seeing this, for example, when hospital centers move from totally analog workflows to increasingly adopting digitization in their workflows. So for example, maybe every specimen is just routinely scanned that passes through the pathology department. Then pretty quickly you'll end up with a database of hundreds of thousands to millions of digitized H&E images. So that's obviously exponential growth in number of images. At the same time, though, we're also seeing, the data is increasing in terms of the amount of information contained within each image. So this is thanks to, technologies like, multiplex immunofluorescence imaging, where instead of 3 channels for a bright field, white, light, red, green, blue image, now we can run panels with, 7 channels for Vectra, or, upwards of, 50 to 100 channels for something like Codex, spatial proteomics. So in these cases, by scaling up the number of channels and the amount of information actually contained in each image, that's another dimension kind of this move towards big data. And so when we're kind of putting together our plans for how we're going to support digital pathology at Dana-Farber, you know, it was a key element to make sure that everything in our strategy scaled in both dimensions. And so obviously each dimension, kind of large N and large dimensionality, they both present different opportunities and different challenges and require, you know, different complementary, but sometimes different ways of thinking about the tools. So there were a lot of, you know, open source image analysis and machine learning libraries that are out there. It's a very, you know, robust community. But when we, you know, embarked on this journey a few years ago, we realized that really they were all kind of lacking for specifically the field of digital pathology. So these are just a few key reasons. You know, one, they assume small natural images that can fit in memory. Obviously, that doesn't really apply when you have a whole slide image that's 100,000 by 100,000 pixels. There's also, yeah, limited support for, you know, images that don't have 3 channels. Many of these libraries are just built around, you know, RGB images and just can't really handle, you know, an image with 6 or 7 channels. And then the last piece is just lack of pathology specific algorithms like stain deconvolution or, you know, nucleus detection, fold detection, things like that. So the last piece before I really dive into the methods is talking about kind of why we decided that we needed to, you know, start creating this software library. And the reason for that is because, you know, like Renato mentioned, the first kind of phase of the transition to digital pathology was all data engineering. So in other words, taking the images from the scanners, putting them into the cloud and making them available to our researchers. But, you know, we started to realize that actually that's not enough. You know, we can't just dump, you know, 100,000 whole slide images to one of our researchers and say, here, you figure it out. So actually, in order to kind of unlock completely the value in these images, we actually need to also provide kind of a tool to help our researchers kind of, you know, be able to start incorporating digital pathology into their work. So here I just kind of laid out some of the requirements that we were looking at when we got started. So, you know, important ones, like I mentioned, scalable and multiple axes, easy to use for researchers is obviously super important. Many of our users are not data scientists or software people, so we had to lower the barrier to entry as much as possible. And then the other important part, which I'll touch on a little bit later, is integration with other tools in the open source ecosystem. So yeah, that's kind of to lay the stage for kind of diving in the next few slides into a little bit more about how PathML actually works. So first of all, just to kind of hit this point one more time, these whole slide images can be absolutely massive. And I'm sure all of you know this, but, you know, a typical whole slide image can easily be 100,000 by 100,000 pixels. And like we mentioned, many of these, you know, general purpose tools just aren't really built to work with these types of images. They're oftentimes too big to load all at once in memory at full resolution. You know, let alone feed into another memory hungry neural network or something. And then, yeah, it's the same exact story for these massive, you know, multiplex immunofluorescence images. So to get around that problem, you know, one of the most standard approaches right now is to actually first divide the image into tiles. Where, you know, we're taking this 100,000 pixel image and we're chopping it up into tiles where each tile might be, you know, 1,000 pixels or 250 pixels. And the point of this is that each tile then becomes more of like a manageable size. And so you can then, run individual tiles. You can do a forward pass to your neural network. You do lose some of the information by, chopping it into tiles, but, there's clever ways to make up for that and kind of learn from the relative positions of different tiles. And so, yeah, I just wanted to mention this because this really forms kind of the backbone of, a lot of the common practices in digital pathology research. So in PathML, how do we design pre-processing pipelines? So in other words, you chop the image up into tiles, then what's next? Well, you're gonna wanna do some type of processing at the tile level. And so in PathML, the way we think about this is by really kind of building a pre-processing pipeline, where we define a pipeline as basically a sequence of different transformations or operations that are applied to each tile. So just some examples could be, stain deconvolution, nucleus detection, pen mark detection, etc. And there's a lot of different transforms that come built into PathML. So you can kind of just mix and match them to put together any kind of custom pre-processing pipeline. And then the other exciting part is that anyone can define a custom operation and then kind of just slot it in next to any of the built-in ones. So with this framework, it's kind of like a way to generalize nearly any type of tile level pre-processing pipeline that you might want to apply. So here at the bottom, we have just a few examples of different types of transformations that can be, fit into this framework. So we have, classic image analysis things like blur or, superpixel interpolation. Here's, some pathology specific algorithms like H&E stain normalization. We can also run segmentation models in these pipelines. So, here's just a basic tissue detection model. Here's a neural network for performing nucleus segmentation. And then we can also add kind of metadata and process the image. So for example, here we have an example of an immunofluorescence image where we're actually quantifying it and then producing a counts matrix at the tile level. And then here's kind of the same thing, but then also phenotyping the cells using a rules-based approach. So pretty much any type of operation where the input is a tile, the output could be, a modified image, a mask, metadata, etc. Anything that can fit into that framework can fit into this this modular pre-processing pipeline framework. Okay, so now how does it all kind of fit together? So first you start by just loading the image into this kind of slide data object. So, we like Renato mentioned, one of the key challenges is this proliferation of, vendor specific proprietary idiosyncratic file formats. So that's a huge headache. So we have 3 different backends for actually loading these images, which allows us to support, more than 160 of, most of the common image formats. And this is thanks to bioformats, OpenSlide, again, the open source efforts that we're really building on with this. And then, so once you've loaded the image into the slide data object, then you construct your pre-processing pipeline using this kind of modular approach that we mentioned. And then you run the pipeline on the image at the tile level. So here is kind of where, a lot of the magic happens, so to speak. So first of all the tiling, in other words, taking this, 100,000 pixel image and chopping it up into smaller tiles, all of that happens behind the scenes. So the user doesn't have to, be writing that tiling code from scratch every single time. The parameters of the tiling are completely flexible in terms of tile size, tile stride, so the number of pixels between each tile, overlap between tiles, etc. And then the other, super important part for efficiency of processing is this idea of parallel pre-processing. So in other words, because each tile is being processed by the pipeline independently, we can actually be processing multiple tiles at the same time on different machines. And so if you have a cluster of computers, for example, this really can help increase the efficiency of evaluating running the pipeline on thousands or tens of thousands of tiles, because you can distribute all that work across a cluster of workers and then aggregate it back together at the end. So to do this, we use this other open source tool called Dask, which is basically a distributed computing scheduler and manager. Again, open source in Python. And this lets us support all different types of computing environments, ranging from a local machine, so like just your laptop, all the way up to big high performance computing clusters, and then also cloud computing clusters like Kubernetes and things like that. So this is kind of the key to how we speed things up using this distributed computation. Then after all the tiles are processed, they go back, they're written to disk into this H5 path format, which is built on another open source tool called HDF, which basically allows for efficient storage on disk of data and then accessing the data without having to load the entire thing into memory. And then from there, we provide a data loader for interfacing with PyTorch and other types of downstream machine learning models. So this is kind of at a bird's eye view, kind of how image analysis pipelines in PathML are kind of laid out. And again, this framework generalizes to H&E images, immunofluorescence images, spatial omics, etc., all in the same kind of framework. So what does this actually look like for a researcher using this tool? Well, like Renato mentioned, what we're able to do is reduce workflow that would take tens of thousands of lines of code behind the scenes to 10 to 20 lines of code. So what this really does is it lowers the barrier to entry for our researchers that we work with who want to get into digital pathology, computational pathology research. So here's kind of a real working example of what this looks like. So here I've kind of taken the 5 main steps of the process. So first, loading the image. It's just a 1-line call to PathML library. The second step is defining that modular pipeline from a sequence of different operations. Again, it's just basically a 1-liner where you just lay out in sequence the different operations you want to apply. Step 3 of running the pipeline with distributed computing using Dask is again just a 1-line call. Saving the output to disk in this H5 path format, again 1 line, and then getting the data loader for interfacing with any kind of PyTorch machine learning model is again just 2 lines of code. So this really this is kind of the key of why this has been, a useful tool for our collaborators, is because it just really lowers the barrier to entry, where, you don't need to be a professional software engineer, professional data scientist in order to start putting together really these cutting edge pipelines. So that was kind of the nuts and bolts of how PathML actually works. So now I just wanted to talk about kind of the state of the project. So, like Renato mentioned, this has been a totally open source project from the very beginning, meaning that all the code is available on GitHub. We, excuse me, we welcome any users, anyone who's interested in collaborating or using this in your research or giving feedback. That's very welcome. It happens on our GitHub page or to our email. So far, we're at more than 200 stars from the GitHub community, and we've reached more than 18,000 downloads from the Python package index, or PyPI. Currently, PathML tools are being used in more than 5 different labs and groups between Dana-Farber and Cornell that we directly collaborate with, plus 2 imaging core facilities at those institutions. And then again, these are just the people that we directly collaborate with. And then there's people, really around the world who are engaged with PathML and through the open source community, finding bugs, asking questions, making suggestions. So that's been pretty exciting to see. And then also, yeah, we're just this is, one tool that we have been building for the last few years, but it's really part of this, what we see is kind of a growing ecosystem of digital pathology open source tools. So there's lots of other similar, efforts from other institutions. And so for us, that's like pretty exciting because it shows that this is a really important area, and it's really that kind of cross-pollination of different ideas and different approaches that will help the community the most. So here for the last slide, I just have a few examples of how our collaborators are using PathML in their work. So again, just to highlight kind of the range of different applications that this type of tool can be used for, depending on the use case. So we have people using PathML for, machine learning for H&E whole slide images, where you're looking at multiple instance learning, in this case, predicting ERG fusion status, mutation status from the H&E image. So that's using kind of some multiple instance learning approach. And then for the high attention tiles, they're using another machine learning model to look at segmenting and classifying the different nuclei to try to understand, what's the model kind of looking at. Here in the middle, we have an example of an application to the 7-channel Vectra immunofluorescence images, where again, we have kind of, PathML is being used for image processing, cell segmentation, rules-based phenotyping of cells, and then spatial biology analysis of kind of how these tissues are structured. And then the third piece is kind of a different application that's more of an institutional type of resource, where we're actually building and deploying image analysis pipelines to the molecular imaging codex core at Dana-Farber. So this is, an example of deploying a pipeline, not for the research setting, but more kind of one step abstracted to support dozens of researchers. And like Renato mentioned, we're able to increase the efficiency compared to their existing pipeline by about factor of 10. So if we have a couple minutes, I also wanted to show kind of, this is our documentation. Can everyone just give a thumbs up if you can see? Okay, good. Yeah, so this is our homepage, which is at PathML. You can go to pathml.org and navigate here. And this I just wanted to show because for anyone who's interested in learning more or kind of seeing some more like worked examples, documentation, etc., this is probably the go-to place. So on the left side, we have just some kind of like descriptions of different steps in the process. We have, documentation of how to load images. And then if you scroll down here to the examples section, what we have is a bunch of, fully worked end-to-end examples. So here's an example of different types of images that can be loaded in PathML. So kind of just highlighting like how we support, a bunch of different image formats ranging from, again, just big whole slide bright field images to kind of spatial omics images and you know, even some kind of time series volumetric images. Here we have just a pretty basic example of getting started with bright field imaging. Again, just working through the process that we described of loading the image, building a pre-processing pipeline, running the pipeline, and then loading it into a PyTorch data loader. And then we have, you know, fully worked pipelines for loading and analyzing and studying, you know, everything related to codecs, spatial proteomics. So I just wanted to highlight this because it's a great starting point for anyone who wants to kind of learn more and start diving in. So yeah, this is kind of what we wanted to highlight today about kind of our journey for building PathML, kind of how the framework works. It's efficient. It provides a unified, streamlined analysis framework for H&E, IHC, you know, fluorescence, spatial omics, etc. It integrates with many of the common tools from the, you know, the machine learning ecosystem like PyTorch, TensorFlow, JAX, plus integrates for, you know, spatial biology, integrates with ScanPy, SquidPy, other tools from kind of the single cell and spatial analysis ecosystems. And then, yeah, head to the website to check out any of the documentation. This is probably the most important slide, which is, you know, to really give a shout out to everyone who's been involved. This has been, you know, a huge kind of team effort that's happening between Dana-Farber and Cornell, and again, just the broader community. So yeah, I hope this was useful. And I guess at this point we can turn it over to back to you, Joe, in case, or if there's any questions. And yeah, thanks everyone.
Fantastic. First, of course, the applause. Thank you so much for taking us through. I see David Clooney is on. David, do you want to ask the question or want me to read it? I don't know, I can read it. Do you have an interest in testing PathML with more DICOM whole slide images? I think you can
Yeah, sorry, I was going to respond verbally, but I was on mute. Jacob, I was just wondering if you were interested in collaborating more actively with sources of DICOM images. So, for example, I work with the Imaging Data Commons project, and we have converted all of the CPTAC and TCGA and NLST slides into DICOM form and make them available for cloud computation. And so that would seem to be a fairly natural fit with your pipeline and tools.
Yeah, certainly. I think that would be a great collaboration. Maybe we can, you know, connect via email or something to discuss more. I know that DICOM has been, you know, a key focus for many of our, you know, researchers and our collaborators. Renato, do you want to jump in more about that too?
Sure. Yeah, no, I'd say the more data we can connect, the better. I think we can, we have an API for accessing data sets already in PathML. I think that would be one way, maybe pointing from inside the library, load the IDC dataset 123, something like that would be very nice. And similarly, if you're thinking about having a link to PathML on your website, so that when you give data to people, you also give them, hey, this is also a software toolkit that you might evaluate, so that you start not from zero. You know, it takes you 0 to 60 at least. So I think, yeah, something in that realm, or if you have other ideas, very open to that. Absolutely.
Sure, I'll connect with you by email.
Thank you.
Fantastic. I presume, you know, seeing who's on the call, you may get a few extra downloads from within the FDA and or friends.
I had a question, Joe.
Of course, Brennan. Hey, good morning.
It's about maybe not DICOM, but the flip side of DICOM, everything else. How do you stay current with all the different formats? I heard you mention you build on bioformats, for example. When you say that, are you talking about the libraries that they have, and how often do you have to update according to their updates, and how do you monitor all that?
Yeah, so that's a great question. So yeah, we haven't written all of that from scratch. So yeah, we're really building on top of the bioformats and Python bioformats. You know, bioformats is in Java, I guess, and then there's another library that provides a Python bridge to the bioformats library, and that's what we build on top of. So, so yeah, updates to bioformats. You know, as long as our dependencies also update, then we'll just benefit from those. I hope that kind of answers your question.
I'm just curious, how often do you see those updates, and whether they cause any problems downstream, considering that you're juggling so many formats?
Yeah, so we haven't like seen any like specific problems I can think of that were connected to an update to bioformats or something that then broke something downstream. But you know, the only thing I can say about that is that we do have a pretty robust testing suite that's run, you know, routinely on PathML to make sure that basically, obviously, it's not 100% foolproof, but just to give us, you know, more confidence that the code that we're seeing is not broken and actually is functioning. So we have tests to kind of run through some workflows and specific checks to, again, try to identify things that break as soon as possible. But that hasn't been a problem that we've noticed so far.
Thank you.
Maybe I can speak a little bit also on that. When we do our imports, Brandon, we do with respect to a specific version of ScanPy, bioformats, and all the other libraries. That means that we know exactly what version of the upstream library we're getting, and we also run all the tests that Jacob mentioned. So there isn't just a pass-through. When they do a major upgrade, then in the development branch of our software, then we start testing with their new version. And if we see that nothing breaks, all the tests pass, and there is backward compatibility and forward compatibility, then we upgrade and we keep an eye on that. So far, as Jacob mentioned, we've been very diligent using software engineering best practices, and that really served us well. Since 2019, when we started PathML, I cannot think of any real issue with other dependencies. Exactly for this reason, we basically kept them fixed until we were ready to upgrade, which is something that we do maybe every 4 to 6 months or so.
Yeah, and I guess just another thing that I'll jump in with is that, you know, because we've built this library kind of modularly, so we have, you know, several different backends. So one is built on top of bioformats, one is built on top of OpenSlide, for example. So what that means is that they're all tested individually. And also, if we ever need to, we can just write a new one, you know, if there's some new library, or if we need to refactor something, we can just kind of slot it in alongside the existing ones. And so it would streamline the process of having to refactor or update in the future, you know, if it comes to that.
Good. Modular is good.
Have you done some testing? Because I mean, I can tell by GitHub stars and downloads, etc., that the community is growing. So that means, you know, people are adapting it. But have you considered some formal assessment, you know, in terms of time savings? That if you, I mean, I was very impressed by the, what is it, like 9 lines that you need to kind of put all the different buckets and functionalities together. I mean, that must be much faster in terms of, you know, accomplishing, let's say, a machine learning task. Have you considered like generating data to see what that would take in a non-PathML solution?
Yeah, I think that's kind of a little bit hard to quantify maybe, because we're kind of looking at like the counterfactual of like someone who's able to start doing digital pathology research using PathML, like the counterfactual to that would be they just don't do digital pathology research. So I think it might be hard to, at least, just for some of our collaborators that I'm thinking of in particular. So I think that's a great idea to try to quantify that. I'm not sure how we could do that, and it's not something we've looked at to date, but yeah, that's a great suggestion.
I'm just, trying to, I mean, I know how much work it is to make, let's say, all these components work together. That's the computer science part of it. What I just realized is it is very hard to understand for someone who hasn't suffered through pulling slides, putting them on a file, taking screenshots, snapping images, even if you find a region of interest, annotating it, downloading this, right? Just that first initial, like, let's say, step takes months to years. And, now it's basically more or less a conduit to say, yeah, now we can start talking about the analytics part. We don't have to think about the image formats, etc. But that's very hard to quantify and make sure that people understand what a quantum jump this is. I presume David had some similar experience with DICOM, right? Once the once the transition is made, it's very hard to like retrospectively. I think counterfactual is like a good point of saying that. What is the comparator for something like that?
Yeah, if only we lived in a world where there was one standard pathology format.
Yeah, I hope we can get there soon. Well, we'll see. It would certainly make our life easier if we only had to focus on supporting one image format instead of, having to kind of piece together all these different things.
I have another question that's sort of related to experience with different file formats, but is to do with tiling, which was mentioned several times as being critical for feasibility, but also an essential step to, shall we say, perform. Given that most of these source file formats already tile the data or arrange the data into strips, if not tiles, do you find that retiling results in a loss of fidelity because you have to decompress the already compressed tiles? And the converse of this, in essence, is, what's the problem with the original tiles? Are they too small? Are they too big? Or whatever? Because people have opinions about what's the sweet spot for the tile size for certain kinds of computation. And, and a Perio SVS file might have a 240 by 240 tile, and somebody wants a 1024 by 1024 tile. And does this decompression from the lossy compressed JPEG source format cause any negative effect on the downstream computations because it's not the same data anymore?
Yeah, that's a good question. So yeah, I guess to hit on your first question, the reason we wanted to support this kind of different options and flexibility for tiling is, like you mentioned, specific tile size can actually be important. So, like one tile format might be tiled at a certain size of tile, but you want to use a downstream machine learning model, which only was trained on a different, so if the machine learning model requires, 299 pixel tiles, then that's kind of a hard requirement that then has to be propagated back to the tiling step in the pipeline. So that's kind of the basis for that. And then also the other key part is thinking about, we wanted to support also overlapping tiles, and really we, as the people making the tool, we didn't want to be prescribing to the users like what's the best approach. So that's kind of the motivation for why we made it so flexible. Yeah, so for supporting different sizes of tiles, it's not something we've evaluated, whether, if you're using a tile of an image format that has tiles of size X, whether X is then that's the best size to use for downstream analysis, from an analysis point of view. That's not something we've looked at, but it could be, certainly it's interesting. It sounds like there might be something there. Other types of formats, like for example, for some formats, we just serve the tiles directly from the image. So like in our implementation of support for DICOM, for example, we just, give the I think they're called frames or like the tiles directly from the DICOM, and we offer less flexibility to users and, doing the overlapping and things. So yeah, really it's kind of a mixed bag, but definitely something that's important to keep in mind and that we'll, keep looking into. So yeah, thanks for mentioning that.
I haven't seen any studies on that. Sorry, Renato, but that's probably important from a regulatory perspective, right? Go ahead, Renato. Sorry.
I just wanted to say that absolutely, it's a great point, Joe. The one about tiling. You can think about it in a couple of ways. One thing that we have seen is that, for instance, for codecs, there are multiple ways to decide the tiling, do it and undo it. There are good algorithms, basically, to evaluate how to best assess the tiling, what shape you want to use in your tiling, and all that. Since we are looking at pipelines that are only 20 to 50 lines of code, you can think about tiling as something that maybe is part of your hyperparameters. So you make that yet another thing that you optimize in your downstream AI, meaning you cycle through this pipeline enough times until you come to the best optimized decision for shape of the tile, how big is it, how to do it, how to do it, and all that. So pretty much similar to all the other hyperparameters that we have downstream in the machine learning and AI, this could be, another thing that we iterate upon in a grid search or Bayesian type of search when we do our hyperparameter optimization. It's just an idea, but yeah, just to say it's an absolutely very good point that is raised. Would love to collaborate on that.
I had a question. You mentioned I think this was related to a colorectal cancer research where you used 7-channel IF images. I can possibly imagine who that's coming from, but my question is mostly, so if you use PathML to, let's say, train or learn, have you looked into also back propagating some of the features or, image modalities, or do you leave that up to the user? Meaning, how do you visualize that? I mean, that's almost like a separate market or separate, software suite, but I was just curious how you deal or
Yeah,
conceptualize
so
that.
I can pull up we have some bonus slides to kind of dive deeper into that example. Maybe I can just put up for a minute. Oops. Yeah, so here's just, to kind of walk through that example. This was, one of the early adopters of PathML, which is Maria Diaz-Meco and Jorge at Jorge Moscat Guillen over at Cornell. So, this is kind of this is their experimental workflow. So they have, these images from the colorectal. So this here at the bottom was the PathML type of pipeline that we designed. So going from the raw image, spectral separation and deconvolution happen in the software and the instrument. So we don't actually do those, but then segmentation of the cells, quantification of the cells into a counts matrix, and then phenotyping, and then spatial analysis of the tissues. That's all happening in PathML workflows. So this is another example of how we actually integrate again with the open source community. So, using segmentation models that are already existing open source. So this one is the Mesmer model that we use, which is from David Van Valen's group over at Caltech. So we just, in PathML, we don't reinvent the wheel. We just provide an integration with DeepCell Toolbox for doing these types of tasks. So this is kind of, example of how the cell segmentation works. And then once you have all the cells segmented, then you can actually set up rules and do kind of phenotyping of the cells based on their expression of different markers. And so here on the top is kind of the, the composite image of the of the original image, and at the bottom is kind of the cells color coded by the phenotypes. So then, the reason this is super cool is because, now you have not only the marker quantifications of each cell and the phenotype of each cell, but you also have the location of each cell. So then you can ask like real biological questions. Like in this case, they're looking at, are T cells differentially enriched in the neighborhood of PKC, lambda, iota, negative epithelium? I don't know like what that means from the data science perspective, but that's an example of how, molecular and cell biologists are using these tools to now ask biological questions. And yeah, this is all using functionality that's, included in PathML. So yeah, I hope that answers your question a little bit, or at least gives a little bit more context of like what this type of workflow looks like in the cancer research setting. Yeah, thanks.
No, absolutely. I think the one thing is of course to train models, and then the other thing is like to backpropagate it in a way that a pathologist or researcher can actually analyze it and derive either new or different meanings from it. Um, yeah, I think you may have heard this weekend at the ASCO meeting, the HER2-low story was presented, right? Which now puts on the map quantitative histology basically for treatment decision making. Initially was just whether HER2 is positive or negative. Now we have to distinguish between low and negative and or positive. So I think some of these more simple quantitative methods are probably hitting the clinical space, so probably still a bit to go until machine learning will hit the clinical domain, but the first algorithms have been approved. The question is when they move forward. So I thought it was very interesting to hear how you have like a production and then a, let's call it like, or in production versus a development version, right? That's basically already like change protocol. So that's definitely good software development practices, but I think it's kind of similar to, how we deal in the laboratory with new tests. Any insights on that? How do you handle your management, your quality management system about the code? Because it must be quite enormous now, and it's a big
Yeah.
team, so maybe just some insights there.
Yeah, so basically we just use kind of standard like software engineering practices. So a big one is test-driven development. So in other words, having a really robust set of unit tests and integration tests where, basically we tried as much as possible to verify that each individual piece of code that we write is actually doing what we think it's actually doing. And then we have a test for that. And then, every time we find a new bug or a new like behavior that's unexpected, we'll fix it. Then part of the fix is actually writing another test to make sure that we always catch it if it happens in the future. And then we also have processes in place to make sure that, when new code is added to PathML, that first of all the tests have to pass, new code has to have new tests, and then every request to merge code has to be reviewed by someone else. So just to kind of add as much redundancy as possible. And then the last step is that, we have a separate development branch where we kind of use the test bed for code, and then only when we're like totally satisfied that it's all working, all the tests are working, everything makes sense, then we'll actually merge it into the main piece of code, and which is actually what gets published. So again, it's not perfect. I don't think there is a way to have like a perfect system, but we're working in that direction to try to have good quality control. Yeah, it's very important.
Oh, that's very good. Other questions from the group?
I just had a question about what you all, going back to like this, trying to scale up the end value, how to what you would like to see from pathology departments, and like what would all pathology departments in your eyes be doing to make to like increase like the global in value of scan slides?
Yeah, I think that's a great question. That's from our perspective, we're typically, as the data science, machine learning side of things, we're mostly working with images that have already been digitized. But I think you're getting at a really important point, which is that there's a lot of work that goes into kind of that first transition of going from an analog workflow to a digital workflow. So going from, this top, the blue workflow to just the light blue workflow of where, having processes in place to, be routinely digitizing specific cohorts, if not every image, or, having, funding to buy scanners and to pay for, technicians to be operating, scanning images. That's kind of happening upstream of us at the pathology department level. And I know that there's a lot of, different components that go into that, but that's obviously a key prerequisite for anything we've been talking about machine learning, digital pathology, is having images. So yeah, super important.
And maybe Jacob and Jared also to build a little bit on that. We are fortunate enough that we know personally some of the people that some decades ago put together the DICOM consortium. So before DICOM was a thing, before it was an image standard and a communication standard, there were so many ways that these radiology machines were communicating, were storing, and then eventually there was a regulatory distributed more than centralized effort where hospitals said either your scanner also reads and writes this thing or we won't buy it. And that was the thing that eventually forced the industry to adopt one standard that allowed for more adoption of the technology. So standardization, Jared, to go back to your point, is is still something that we can improve a lot upon in the computational pathology. It's really disconcerting to see 160 data formats. Really, how's that even legal? Sometimes I have this question in my mind. Why do we have encrypted fields and all that when we buy the scanner? So I think there is room for that. Which is just very standard in many other parts of the same industry. So it seems that that is one area where we can improve. The other one would be maybe cross-training. It's very hard to find people with Jacob's background in data science, and they are also pathologists. I count very few. That's why PathML was designed by pathologists, but implemented by Jacob and others with more of the software and data science skills. So I would say cross-training would be also something that could be very, very important. As a part of the pathology fellowship, it would be amazing to get kids also started with, and I mean kids, these young professionals also started with the basics of AI. And recognizing what a AI problem is versus it's not, what are best practices to do certain things, and even just get them started with some computational tools. Basic introduction to Python would be better than nothing, and get them started on some of those techniques. I think these are the two things, both on the regulatory side that can be centralized or distributed, as well as on the training side for future generations.
With those words, I thank both of you for the presentation. This was a fantastic session. As always, we put this up on the website. If you could share your slide deck with us, that would be great. And thanks a lot, and keep up the good work. This is really phenomenal. Thank you so much.
Thanks. Bye, everyone. Thanks,
everybody.